we will be discussing another basic application of moment distribution method to a frame, right? So probably we will have some yes, we can go with that share. And yes. So since we covered all the fundamentals in the first video, we shall start with the example too, right? So if you didn't watch that, please watch it because all the fundamental concepts are there, right? So we will do an example with a frame, right? So we shall start here. Right. So I should do a frame. Okay, so yeah, I will put a support. So I'll name this as A, B, C, and D, E, and F. Okay, so I will have a UDL probably on here. So I would say 6 kilonewtons. So don't be upset, it's just always come to my mind. It's 6 kilonewton because it's easy to simplify because the fixed moment is W is 12, so it gets cancelled. That's why. So here I would have bending moment of how much? So I will apply. Yes. So here I will apply how much? Just 16. So it is also divided by 8. That's why. So I can go ahead and yes, I will apply. So this CD part is a cantilever. Right? So at the end, you will have a load probably of let's say how much? 2 kilonewton or 5, whatever. Let's say yes, 5 kilonewton. So this is the frame, right? So if you didn't watch the video, please watch the video one. for moment distribution because all the basics are there, right? This is important, right? Right. So I will take these lengths as this is 2, this is 2. Oops. So this height is also 2. This length, let me take it 1. Okay. So this is also how much? I can take this 2, right? The length is 2. So it's not given. EI is constant. So that's not problem, right? EI is a constant for each member, right? So L is given, right? So now first I need to find is this continuous, fixed, or whatever, right? So as we discussed earlier in the video, so if you show a fixed term, so it is directly fixed, right? And as this well, right? No need to worry. And you have this member is stop member stops here, so that is has not continued all the support. So on the other hand, you only have one bending moment of this member at this joint, right? So that's going to be anyway 0, the final bending moment. So that's why it is discontinuous, right? So these two have 3 members together connected. So that means sigma summation of bending moment is 0. That means a continuous end. So this part we need not to worry. Why? It's a cantilever part. It's a special one. So I on purpose uh, considered that. Why? Because this part is determinate, right? If you apply such moment, right? So this is going to be in this shape. So the member will resist it in this way, right? So we know the bending moment, right? We already know the final bending moment, so no need to use that part. What is the bending moment? Load into the distance, right? M is 5 into 1, 5. So it's in the anti-clockwise direction. So I have marked it. So I don't need to mark the negative sign again. Okay. So I'm taking usually clockwise positive. Okay. All right. So yes. Now this part, if you have a cantilever part, you should not be afraid, right? You should be happy because you are lucky, right? Those parts already solved. Nothing to worry, right? No stiffness needed for this part, anything not needed. So this is, you can forget about it until the end, right? You know the value M, that is MCD, right? And MDC is the free end, and you know free end, what's the bending moment? The free end cannot bend, right? So it's 0, right? So you don't need to worry that. And yes, so we can take this sketch Okay, bit larger. So sorry. So you saw this is fixed to continuous, right? So if it is fixed to continuous, this is 4ei over L. So my L is 2, right? For EI. So EI is constant for each member. So that means this is going to be EI over L, right? This is 4ei over L, the stiffness. This is K CF. This is K BE. Is that right? Yeah. This is K BC. That is also continuous to continuous for EI over L. EI. This is also 2EI. So what about this? This is 3EI over L, right? So you should be careful on this. K AB. So L is 2. That's going to be 1.5 EI, right? And this part we need not to worry, right? Already solved. Already solved. This moment and this moment, right? So that's done. So I need to find the distribution factors now. So I will put the distribution factors in red. So distribution factor simply means how much bending moment that a particular member can take at a joint, right? From the total, if you consider the total members, right? So here, there's only one member, right? Team. So at the fixed member, you know, distribution factor is 0. You know how that's done, right? So we proved it in the previous video, right? So in the basics video. So here if you apply bending moment, this will take some amount, this will take some amount, this will take some amount. That some amount is equal to the distribution factor, right? So here you don't need to worry because this part is already no need to worry, right? So important fact here, we only consider these two members because the cantilever part already solved. We know that, right? Here you only have one member, so that means P in the discontinuous and the distribution factor is 1, right? So I need to know what's this here, here, right? So distribution factor BA, it's 1. So that's going to be, so the stiffness of that member is KAB over the total stiffness, KAB plus K, this beam is joined. So that means KAB is coming. sorry, KBC. And KBE is coming. So I'll write this. How can I forget that? So yes. So KBE. So that's going to be 1.5 EI over 1.5 EI plus 2 EI plus 2 EI. So what's this value? Will be 1.5 over how much? 0.5 over 4 plus 5.5, right? So that's going to be 0.27. Right. So the summation of distribution factors is equal to 1, right? You know that. And you can just reduce this 0.25 and the remaining would be how much? 0.72, right? 73 actually. It's okay. Right. So this distribution factor is evenly distributed for 2 and 3. Why? Because the member is same stiffness, 2EI, 2EI, right? So the amount taken by this member at here is carried out by this member as well here, right? So this is usually lower stiffness, so that will take lower value. So this will have, so the distribution factor for BE equal to distribution factor at BE for BC member. So this is read by this is read as distribution factor at B joint for BE member, distribution factor at B joint for BC member, right? So it is not equal to distribution factor CB, right? But the KCB and KBC are equal. Those are fundamentals, right? Because the same member stiffness, but the distribution at the ends are different, right? It depends on the members connected at that joint. So it's going to be 7.3 over 2. So this is equally distributed by these two members. So 7.3 over 2 means approximately 0.36. Right. So here both members have 2EI and 2EI. So that would be distribution factor would be 0.5 for each member. So that's going to be 2EI over 2EI plus 2EI. And for the other member as well, 2EI over 2EI plus 2EI, right? So that's going to be 2EI over 4EI. And altogether it is 0.5, right? So I have taken the necessary adjustment 0.5, 0.36, and 0.27. The one I required. So say that here the distribution factor is 0, distribution factor is 1, 0, right? So I'm okay, right? So I need to find the fixed end moments, right? So you can find, so only you have loading in these members 6 and 16, right? BC and I haven't given you the, so it's acting at the middle. Okay, so it's 1, 2. Okay, so the fixed moment at BC is equal to, the appendix you used earlier, right? So it's minus WL squared over 2L. So the appendix was used in the first video, right? You remember? So it's 2L, right? Why minus? It's anti-clockwise, right? So it's going to be, this is 6 kilonewtons per meter squared. Sorry, meter minus 6 into squared over 2L. So that's going to be 2, right? So M so MCB so yes, you have here MCB as WL squared over 2L. So we can apply here again. So it's going to be same but positive. So positive means it is clockwise direction, right? So here, just let's say like this. So you can rotate this and see if it is, so rotate this by 90 degrees and see. So it's going to be like this. 60, right? So this is E, this is B, right? So your fixed end moments EB is going to minus WL over 8. So that's going to be minus is the anti-clockwise, right? L is 2 and this is 8. So this is going to be 8, 16. So that's minus 4. So MF, this is EB, MFBE is going to be same but positive. Therefore, so those are my table. Now my distribution factors are done. So stiffness was done, stiffness are found. So distribution factors are found. So fixed end moments are found. So that means I can go ahead and do the table, right? So the table will be a bit large. So I need to go with it. Sorry about that, I'm using a mouse. Right. So altogether you have how much? Okay, 1, 2, 3, 4, 5, 6, right? And for BC you have 3 members, right? This is A. You have just 1 member for A, right? This is B, but B you have 3 members. C also you have first P1, E1, F1. So okay, this is B. This is C. This is going to be D. It's going to be E, and this is going to be F. Right. So I can write here this A, this is B, this is C, this is D, this is E, this is F. Those are the joints we have, right? So here I'll consider the cantilever part, but that's already solved as I said you, right? So here you have AB, you have BA, BC, and BE. 3 members are connected at uh, B and as well as C. CB, what's next? CF, and C, right here, DC, right? So DC and CT, the cantilever part, right? Nothing happens to that. So, yes, EF, so that's EB, and this is F, C, right? Am I correct? Yes. So, yeah, correct. Right. So I can go ahead and write the fixed end moments. Sorry, the distribution factors first. So AB is a fixed pendant that is continuous, so distribution factor is 1. BA, it's 0.27. BC and BE were equal, right? 0.36. And CB, what's CB? It's 0.5 and CF 0.5. And whatever added is taken by these two members. Why? This part is already solved, right? The thing I'm highlighted in the cantilever part is already solved, right? So no need to distribute anything or do whatsoever to these two parts, right? So you know at the cantilever end you have zero bending moment, and here you have 5. It's anti-clockwise, it's negative, right? Why? Anti-clockwise, the negative side, right? Then it's negative. Sorry, the distribution factors are not related. Right? I don't need anything here and yes, right? So E and F are fixed support, so distribution is 0. Here there are 3 members connected, but CD and DC were already solved. So we don't need to distribute anything. Whatever remaining, we can distribute it within CB and CF. Why? CB telling I can take 0.5, so that means 50%. CF take the other 50%, right? So DC also the free end. So that's nothing happens. So that part is already solved. You are lucky, right? So you can uh, yes, you need to write the sorry, fixed end moments. So at AB you don't have any loading. AB and BA 0. Right? For BC and CB, it's BC and CB. Here it's -2. Right? Here it's +2. BC and CB. Right? Here, don't be careful, right? So BC is not just B side of CB. CB is somewhere else now, because you can't draw a table where exactly lies nearby, right? Especially when you have 2 or 3 more joints, right? So you need to be careful, especially when you are carrying over, right? So I have here PE. What's PE? Fixed moment PE is 4, right? So that's clockwise. Here anti-clockwise, right? Anti-clockwise. EB anti-clockwise -4, BE 4. E 4, EB anti-clockwise -4, right? So CF and FC, you don't have any loading, right? So that's basically 0. and DC is the free end of that cantilever. So I will write this because these are final moments, right? So you don't need to do any damn thing for these two columns. 0. And here there was -5. Why I writing in red color? Red color was the final values. So that part is already solved. It's already solved. So if you have a cantilever like this, right? So if you have a load distributed, so the total L is WL, right? If you take this length as L, so the moment is WL into L by 2, WL squared over 2, right? If you have a point load, W into L, the distance, right? So that's a Hoggy moment. So the left, at the left hand side, so that's why it is anti-clockwise. So yes, now we are done. We can start doing the table, right? In the table. So one good question is, where would we need to start, right? So I can start from here. So first I would start, so good practice to start from a discontinuous end. So the discontinuous end is AB, but it's already how to say, already balanced, right? The fixed moment is 0, right? Again, I'm repeating. So these the fixed moments are in red color are the final bending moments, because we are not doing any damn thing to these two columns, right? So I'll start balancing. Where would I start? So I can start. So one more thing. So E and F are also fixed, right? So you don't need to do anything. That you are lucky, right? E and B, F are all there should be a so finally there should be a bending moment, right? M shouldn't be 0. Here sigma M should be 0. Why? Those are continuous joints. So this is the discontinuous joint. So finally the M should be 0, because that only have one bending moment. These have 3 bending moments. The summation, algebraical summation of this should be 0 here as well. So we know one part actually. So the remaining 2 halves. So if you know this is minus x, right? This is minus x. The addition of these two should be exactly plus x. Addition of these two bending moments, right? So that will happen automatically once you solve this. Okay. So yes. Okay, I can start it from B. I will start it from B. So B, so you know this is at here M should be 0 final, right? Here the sigma M should be 0 because it is a continuous joint. Here as well, the sigma M should be 0. Why? C is also a continuous joint. And D, it's a free end, so anyway M is 0. Right? So here it's M is non-zero. Why? It's a fixed end, non-zero, right? These should be your values fine, right? So I can start balancing. So I'll start from here. So here P joint, you have -2 +4. That means remaining part is +2. +2 is, so when you add these two, it's +2, right? So that means clockwise. So our sign convention is clockwise positive, right? So that means clockwise 2 is remaining, right? Clockwise 2 is remaining at that joint. So I need to add anti-clockwise 2 to balance that. That means minus 2 I have to add. So how I going to add that is I need to add, so I'll do it in white color. I need to add minus 2, right? So how, so if you add minus 2, so those minus 2 will be taken by all three members. So BA tells I can take 27% of that, or the other hand 0.27. Okay, BC telling I can take 36% of that, or the other hand 0.36. BE also taking that same amount. So you can just multiply minus 2 into 0.27, right? So that's going to be how much? 0.54. This is negative, right? So this is also negative, should be 36. Minus 2 into 0.36, that's going to be minus 0.72. This is also minus 0.72, right? So now balancing is done. I've balanced B, right? So now I need to carry over, right? So I need to carry over how? So BA's neighborhood carrying over is always done within the same beam, and that means the neighborhood. BA's neighborhood is AB. So that's continuous to discontinuous, right? So A is discontinuous joint, right? So that means you don't give anything, right? You give nothing, right? So continuous to discontinuous, you don't give. But in the other way, discontinuous give half to continuous, right? So that's we are fine. So BC is continuous. Its neighborhood is CB in the same, right? CB is here right now. Okay. So that's continuous to continuous. You should give half. So you should give half to here. So that means negative 0.36, right? Negative 0.36. I won't draw these arrows because it looks confusing. Right? So this is negative. So it's here. Minus 0.36 is shared. So again, BE is continuous and EB is fixed. The neighborhood carrying over done within the same beam, the neighborhood, right? BE's neighborhood is EB, not anything else, right? So you just need to swap the letters, right? BC's neighborhood is CB, BA's neighborhood is AB. It's very easy, right? So BE is continuous and EB is fixed. So you should give half. So that's minus 0.36, right? Now BEC is balanced, right? So you have how much? You have an unbalanced bending moment of minus 5. This plus 2, that means minus 3, minus 3.36, right? So the total bending moment is, if you add these four, you would ended up is minus 3.36, right? So that minus 3.36 is equally shared between these two members because this is already solved, right? Cantilever part, right? So that is already solved. So you can minus 3.36. So if you so CB will take half of that 0.5. So that means 1.68. I would say that is low. I will write that same. So that is minus 3.36. So to balance that, I need to add plus 3.36, right? I need to add plus 3.36 to balance that. And that amount, 50% is taken by CB and 50% is taken by CF, right? So I need to add positive value 1.68, right? Okay. So, so here, now C is balanced, so need to carry over. Balance C and carry over. So CB's neighborhood is BC and it is continuous to continuous. So you should give half, right? So that means 0.84, right? CF's neighborhood is FC, that is continuous to fixed, right? So you should give half. So please watch the previous video if you didn't understand the basic concept. So those are very well explained in the first video. 1.68. So right. So again, now so I don't need to do anything for EV, FC, those are fixed anyway, no need to balance. And CD, DC already solved. And AB, no need to worry, right? So I need to balance B and C at each time, right? So now it's here an additional bending moment of 0.84. So I need to balance it. Why I don't need to add these things? So if you add these 6 values in white color, so those are already 0, right? So it's like you just take 0.84, right? Whatever additional. So 0.84, from that 0.84, 27% is taken by the member BA. That's going to be, so it's 0.84. So you need to add minus 0.84 to balance it, right? So minus 0.84 into 0.27 will be 0.22, right? So it's the remaining part is equally shared between these two members, minus 0.3, right? 0.3, right? So once you do that, again, you need to carry over. So BA, AB, nothing happens from continuous to discontinuous. Carrying over is not done, right? Nothing is given. So BC should give half to CB, right? So it's minus 0.15. So BE should give half to EB. That's going to be minus 0.15, right? So minus 0.15, right? Then again, my again, you can see the C is not balanced, right? Then you need to balance C, right? So this is bit like it's an iterative process, right? Right. So it's an iterative process. So you need to balance now C. So these 6 2 0 minus 5.36 8 1.6 1. So already in balance. If you just add it, it is 0. So you add these values to minus 0.515 means you will be remaining with again 1 minus 1.5, right? So you need to add this value. So how are you going to add it? According to these distribution factors, right? So you can go ahead and try 0.15 into, so that's taken by these two members 0.075, right? So minus 0.15, you need to add positive 0.15. So how? So these two parts will share because this is already solved, nothing happens to that. You need to add 0.075 here. Since it's 0 something, I will stop it. Always good practice to stop at a balance point. Okay, balance C. Right. So now you can if you add these values, so you will see final values, final bending moments, right? Final bending moments. So these are support bending moments, right? So I will write it in another color. So this is anyway 0. So it should be right. That's a discontinuous and bending moment is 0. Here also the free and bending moment is 0. Here the value already solved. It's minus 5. Here it's 0.84, right? So here you can see it's 4 point something, right? 4 plus 0.36 or negative value of these, right? So it's going to be minus 4.51, right? So here it's going to be, so don't add the distribution factors. So things in yellow color and blue color. So just sum it up. So here it's going to be how much? So you can just sum it up what's below this level, right? So add these columns, add these values, add these values, add these values, everything, right? So it's going to be 1.68 plus 0.075. So that's going to be 1.75. It's going to be 1.75, right? Yes, it's 1.755. That's okay. So I will use this is 1.76 then. Okay. So that's going to be 2 minus 0.36 plus 1.68 minus 0.15 plus 0.075. So that's going to be again how much? Have we done something? 2 minus 1.68 is going to be 3 point how much? 245, right? So you can see, you can just see if you plus 3.24 plus 1.76, it's equal to, so this is equal to positive 5. So that is in balance with this anti-clockwise 5. So can you see? It's amazing, right? When you know the concepts well, you can check whether it's you are getting a yeah answer, right? So again, you can go here and 4 minus 0.72 minus 0.3. So that's going to be 2.98. Here it's going to be minus 2 minus 0.72 minus, sorry, plus 0.84 minus 0.3. Is that right? Yes. It's going to be minus 2.18. Right. So this is going to be minus 0.76. So if you add these two, it should be exactly same and opposite to this value. If you add any of these two, right? If you add any of these two, so I would add these two, right? That's going to be minus, so it's plus 0.8, right? So that is approximately equal to minus 0.76, right? So that is in balance. So very slight uh, deviation, right? So if you add one, so if you follow one or two more steps, probably it will converge, right? So now it's time for me to draw this. To draw this, I will consider the rounded values. So this is going to be 0. This is going to be minus 0.8. I would say this is minus 2.2. So this is 3. These are approximations, right? No need to worry. This is 3.2. This is 1.8. This is 5. This is 0. This is minus 4.5. This is 0.8. Right? So I can go ahead and draw this. Right. So I have the loading as well. So just draw the bending moment diagram. So it's here 0. At BA, it's anti-clockwise 0.8, right? So I showed you how to do. If you consider BA, keep your finger on here. So for BA, it's anti-clockwise direction, right? So if I mark anti-clockwise, that means I don't need to put the sign again, right? So here BC minus 2.2. So that means this is totally anti-clockwise. So that means this should be clockwise 3, right? So at CB, it's 3.2. So it's CB. CB means this part, 3.2 clockwise. So CF, it's 1.8 clockwise. So this is altogether clockwise 5, so that should be anti-clockwise 5. So that was the cantilever part we initially solved, right? So pretty amazing, right? Everything comes in a good way, right? Everything ends well. So here it's 0, right? When the moment 0. So EB, it's minus 4.5, right? Right. So here it's going to be plus 0.8, right? FC. Right. Always, some people just, if it is anti-clockwise, some people draw like this. Not even them, I cannot figure out where is the bending moment, right? So don't do this, right? So if it is anti-clockwise, right, or clockwise, keep it like this. So if it is this point for this member, so keep your finger like this. So if it is anti-clockwise direction, so you should have something. You don't draw in this part. You only draw the anti-clockwise direction here. Only half you draw. If it is clockwise, you can draw it in this way. Don't draw here or full thing, right? Just anti-clockwise from here. So clockwise here, anti-clockwise here. That's how you draw it, right? So the moment you do that, you can, so your arrow directions tells you where your point lies on this side of either side of the beam, right? So it's minus, so not minus, sorry, not minus, because I don't need minus. I have taken the side direction. So it's going to be 4.5, I would say here. So it's going to be 3. It's on this side, not this side. It's going to be 3. It's going to be point. So for this part, it's going to lie 0.8 here. So for this part, it's going to lie 0.2 here, right? It's so 0.32 for this part, 0.32, it's going to be here. So here it's going, so I need to go a little bit lower. A little bit lower, 2.2. Say 3.2 is here. I would say 5 is here. Okay. This is C, right? So now here it's also 0. So here it's 1.8, 1.8, I would say something here, 0.8 here. So you need to just so this is your support bending moment diagram, right? So now I need to find what. So these are usually supports are considered to be hogging, right? So always not that way, but usually support bending moments are hogging, right? Obtaining, but can be different as well. So you need to just consider the loading, bending moment due to the simply supported loading, right? So it's only BC and BE, right? It's only BC and BE. BC, I can separate it like this. So it's going to be like this. So if it is simply supported, you know, at end, zero, it's 0. And this is going to be WL squared over 8. And what's that? 6 into L is 2. That's going to be how much? That's going to be 3, right? Yes. So in this part, you have a point load in the middle. So just rotate it and see. Rotate and see. It would be like, right? It's PL over 4, right? You know that already. So that's going to be 16 into 2 over 4. So it's going to be 4. Right? So now so now we are at yes, it's 8, right? So 16 into 2, 2 is the length, right? So simply supported common. So this here it's 0, here it's 0. So these are usually sagging, right? You remember? If you apply like this, your tension will occur on the bottom, right? So it's sagging. At the support, tensions occur on, so these are simply supported, not for this, right? So usually the support bending moments are hogging, right? So tension on the top, right? Those are positive while these are negative. So we need to subtract these, right? So at the ends, it is 0. At the middle, it's 3. And here it's 8. So this is actually negative, okay? Why? These are sagging bending moments. And you just need to reduce it, right? So how we are going to reduce that? So BC, the value was here and ends 0, right? So if you add 0 from these ends, nothing happens. The same point, but you can determine what's the middle point, right? You can just add 3.2 and 0.8, it's 4. Divide by 2, it's going to be 2, right? So you add this value and this value, the ends, and divide it by 2, that's going to be 2, right? So from 2, you should minus, so you should subtract 3. So that's going to be -1, right? That's going to be -1, right? So -1 is somewhere around here. Right? 1. And for here, it's -8, right? Ends 0. So if you subtract 0 from ends, it's 0. But the middle value is, what's that value? So here it's 3. So 3, okay? 3 and 4.5, it's going to be 7.5. 7.5 divided by 2 is 3 point approximately 3 point, it's going to be 3.8, right? 3.8 minus 7.5 divided by 2, that's going to be 3.7, right? So 3.11, I would say 3.8. So 3.8 minus 8 is that's going to be 4.2, right? Is that right? Yes. So why should I take the middle value? So the 8 happens at the middle, exactly middle, and this WL squared O happens exactly at the middle. So I need to know what is exactly at middle. I don't need to worry on these intermediates because I'm drawing an approximate diagram, right? So these engineering solutions are approximate, not the accurate. So we need accurate answers for scientific theories, not for engineering. Engineering, we are worrying about a dependable solution, right? So something which is more closer, right? So this is minus 0.48. So that means it's in the other side because this is going to be 3.8. If you subtract, it's going to be minus 0.48 for 2. Okay. So now you just need to draw this. And here it's a curve, right? So I need to draw that exact curve shape. Right. So it's positive and negative in this region, right? So it's positive and negative in this region. So that will be cancelled, right? So I can just draw the remaining part for each item. So there would be blue color remaining. So that's going to be hogging, okay? So here also, blue color one is remaining, right? here as well, right? Here as well, sorry, out, right? So for this beam, you have the remaining part from the simply supported loading, right? Right. So this is going to be is not canceling because it is the top member and this is the vertical member, right? And here the remaining part would be like this, right? So here the remaining part is like this. So you already know the values, right? So this is your final bending moment diagram, right? So that's this when you know the concept, it's pretty easy to differentiate any of the problem, right? So thank you.